y bar, 1 over the area of our integral of y dA, okay? That's what I mean by centroid, if there's like a homework problem on that. So it's just an invitation to calculate a particular double integral. And let me finish this thought here. So that's two-dimensional. How does this go through? Well, I already told you the average for 3 dimensions, right? How does the centroid look like in 3 dimensions? How do you find the center of mass of a volume? So in 3 dimensions, in 3D, we usually use, oh man. See, in physics, we use rho for density. See the problem? What do we use rho for? Spherical radius. So, thus, we don't use rho, we use delta in here for 3-dimensional mass per unit volume. So the total mass, I have to integrate delta dV over the region E to get the total mass. And then guess what the center of mass is going to be? 1 over m integral over E of x dm. Now, I guess I haven't made it clear yet. What is the integral over x dm? What does that actually, how do you actually carry this out? What does this mean? I mean for you to, in those problems, put dm equals to sigma dA, okay? That's the idea. And so like here, explicitly, what I mean by this is you actually integrate the density, which is a function of x, y, z, times x over dv. And the formula for y bar and z bar is just the same, just replacing the x with y or z, right? This is how you'd find center of mass of a volume. How do you find the centroid of a volume? Same idea, just replace sigma with 1. And the mass becomes not the total mass, but the total volume. So, yeah, you have a question? Okay. Let me see if I have any of these worked out in the notes already. Well, there's at least one example in the notes I want to show you guys. This one's pretty neat. Oh, here's a good example. This is nice for us right now. All right, here we go. So we're going to find the volume and center of mass of the region E. It's essentially the snow cone, all right? But this time not in the first octant alone, but rather what? All the way around, right? So there's a kind of a picture of it. And I'm using the unit sphere for the upper part of the cone. And man, my pictures have gotten all pixelated. That's annoying. But I probably did it to try to keep the size of the PDF overall small or something. I'm not sure that was a good choice. But anyway, what it is, what it is. So here is the center of mass formula for x, for y, for z. We need 1 over m integral of x delta, y delta, z delta, like I was just talking about, all right? And so first of all, we need to calculate the m, which would be the integral of delta dv. And in all 4 of these integrals, we want to use spherical coordinates, right? Namely 0 to 2 pi for theta, 0 to 1 for rho. In this case, again, 0 to pi over 4. Sorry, not to be more interesting. I'll try to be more. I'll be more interesting somewhere. Let's see here. Anyway, so total mass, I've got to integrate my delta dv, which is just this, and lo and behold, 2 delta over 3, 1 minus 1 over root 2, that's my mass. assuming the constant density delta. Of course, if you put delta equal to 1, that's the volume of the snow cone, right? Delta equal to 1 would give you the volume here. Now, oh, like I just say right there. Great. Now, of course, if delta was not constant, then there would be a distinction between the mass and the volume. All right. So the z center of mass is given here by this integral, 1 over m integral z delta. Now the z is rho cosine phi, right? So I do that. dv, again, is rho squared sine phi d phi d rho d theta. And I multiply, I've got an integral of rho cubed, which is rho to the 4th over 4. My theta, d theta integrates to theta. And I've got a cosine phi times sine phi, which integrates to 1/2 sine squared phi. And lo and behold, we've got altogether a delta pi over 4m. And so that's my z center of mass. Is that right? Did I remember to divide by m? Oh, I haven't finished this yet. But m is what? M is this mess up here, right? So I still need to actually divide the m. What's going to happen when we divide by m? That delta goes away. Very good. So, hey, come on. I said page down. There we go. So divide by the m, the deltas be canceling, and some of these numbers simplify, and we get that. So the center of mass is at 0, 0, root 3 over 2, root 3. I guess we could calculate what that is. That might be interesting if I had my calculator. I'm kind of curious. So like the top of the snow cone is where? Z equal to what? Nobody?
It's still radius 9 and 3.
Well, but this one was the unit snow cone. It was radius 1. So the top is where? 1. Yep. You're like, is this a trick question? No, not a trick question. So just 1 is the max z for the snow cone we're considering here in this example. And this calculation, when you run the numbers, that actually works. Oh! Uh-oh. Oh, man. That's not cool. I'm sure this is correct. There's no need to run the numbers on this. It's definitely a number less than 1. So don't investigate it. Okay, so there's an error in here somewhere because I just got like 1.3 for this, which is ludicrous, right? Because certainly the centroid of the snow cone should be what? It definitely should be like inside the snow cone, right? So unless I'm missing something here, maybe I punched it in the calculator wrong. Let's hope for that. What's that? Dang it. So there's an error somewhere in here. I'm guessing most likely the error is like in the last step, the evaluation step, most likely. That's usually where I make my mistake. But another thing I should show you guys while I got this contraption out here. This is a famous example. Everybody should see this. It's a very interesting example. And it's maybe the only improper integral that I'll do in here in the multivariate sense. How would you define a multivariate improper integral? Well, here's how you would do it. There's a couple different approaches, but this is one. At least this is one meaning you could give to an improper integral. Like, what do you mean by integrating this over the entire plane? All right. Well, a meaningful interpretation of that would be like taking the limit as a goes to infinity of the double integral over the disk of radius a. All right. And to calculate the integral of e to the minus x squared minus y squared over a disk of radius a, well, that should yell at you, polar coordinates are my friend. And so the polar dA is r d theta. That's e to the minus r squared. And now we've got an r e to the minus r squared. Woohoo! And for that reason, we can integrate e to the minus... Oh, come on. Seriously? R squared. R squared. R. I paid a student to put these into tech at some point. I feel like it's the student's fault. I can blame them. They're not here. Anyway, so that integral d theta gets to 2 pi. So lo and behold, you've got pi e to the minus a squared. Look, the square came back. Yay. Plus 1. Of course, what happens to this as a goes to infinity? It goes to 0. And so this integral is pi. But on the other hand, we could also look at this integral as they're like rectangular integrals from, say, the symmetric plus or minus a rectangle, cube rather, square. I'm looking for the word square. The square from plus or minus a in both the x and y directions, and let the side of the square go to infinity. Of course, that's actually half the side of the square because the length of the side of the square would be 2a in this context. And if you do that, well, this factors, which then we can pull these apart, and we've really got the same integral 2 times. So we have the integral of this one-dimensional improper integral squared equal to pi. Lo and behold, we have derived the result that the integral from minus infinity to infinity of the Gaussian function, e to the minus x squared, is square root of pi. This is a sneaky trick. And the cool thing is, once you know this, well, then you know it. But there's not a nice way to do this outside of this kind of trick. This is just a fundamentally difficult example. Now, here's a cool thing I should also mention to you. You can modify the previous calculation to similarly show that the integral of e to the minus ax squared dx is the square root of pi over a. And if you know that, there's another trick that you can do, which is to partial differentiate this formula with respect to a. This is known as Feynman's trick. Feynman was a well-known physicist. This was his way to do many integrals. And if you partial differentiate that with respect to a, then you will get a whole host of other formulas which are very difficult to otherwise calculate. But anyway, I think I'm out of time, so I will shut up. But we have a quiz tomorrow, yes? I believe. Tomorrow's Friday, right? So the quiz tomorrow is on change of variables. So you know.